Hello everyone, welcome to third problem solving sessions of linear algebra course. Today's first topic was the kernel and the image of the linear transformation. And our first question is, find the basis for the kernel and image of the following linear transformations. And part A is, T is a linear transformation from R4 to R, where T sends a column to the sum of the entries. First, I want to remind you what is the kernel and what is the image. Kernel T is, recall, kernel of a transformation is then elements of the space T. Let's say T is V to W. Let's say T is a transformation from V to W, and kernel T is equal to elements in V such that T of these V's are equal to 0. So kernel is elements who are 0 at the other side. And image of T is the, as its name, it's the image of the transformation. These are TVs such that these V's are in V. For every V in V, image is the T of V's. Set of T of V's. Now we need to find T of V's for this transformation. Let's look at this transformation first. T of R4 to R, what is that? We are taking an elements here, like x1, let's say x is equal to x1, x2, x3 and x0, x1, x2 and x3 goes to x0 plus x1 plus x2 plus x3. This is our transformation. We need to find kernel and image. Let's look at the kernel. Now we need to find V's such that T of V is equal to 0, right? Let's say V is equal to x0, x1, x2 and x3. This T of V is equal to x0 plus x1 plus x2 plus x3, and which is equal to 0. So there is a relation. So these x0, x1 and x3 are linearly dependent, right? So we can say this one as x3 is equal to minus x1 minus x2 minus x0. So x3 depend on x1, x2 and x0. So dimension of kernel should be one less from the dimension of the space, right? Because there is a dependence in here. So dimension should be dimension of space minus 1. So for example, if x1 is equal to 0, x2 is equal to 0, x1 is equal to 1, x1, let's say first one, x1 is equal to 0, x2 is equal to 0, and x0 is equal to 1. So x3 will become minus 1, right? So our first vector will be 1, 0, 0, minus 1, right? For the second one, let's take this one was the first one. Now we need to find the second one. We need to find third generator. We need to find the 3 generator. So let's take x0 is equal to 0, x1 is equal to 1, and x2 is equal to 0. Then x3 becomes again minus 1, right? x3 is equal to minus x1, minus x2, minus x0. So v2 becomes 0, 1, 0, minus 1. And for the third vector, we should take x0 is equal to 1, x1 is equal to 0, sorry, x0 is 0, x1 is 0, x2 is equal to 1, then again x3 becomes minus 1, so v3 will be becomes 0, 0, 1, minus 1. And this will be the second one. So, by the way, I'm taking this vector as a columns because in the question says t sends a column to the sum of entries. So I'm taking a column vectors, not the row vectors. Now, these are the three vectors belong to this set. Now we need to show that these three vectors are linearly independent and they spans their kernel. Now first thing we need to show that v1, v2, v3 are linearly independent. To show that these are linearly independent, first we need to look at whether they have some relation or not. Let's look at A times 1, 0, 0 minus 1 plus B times 0, 1 minus 1 plus C times 0, 0, 1 minus 1 is equal to 0, which is 0, 0, 0. So, if they are and A, B and C in R. So we will have A and there is nothing in the first row. Here we have A times 0 is 0, B times 1 is B, C times 0 is 0, and here we have A times 0 is 0, B times 0 is 0, C times 1, C, so this is C. Now we have minus A, minus B, minus C is equal to 0, 0, 0, 0. So from here, now from this relation, we have A is equal to 0. From this relation, we have B is equal to 0. And from this relation, C is equal to 0. When the three of them 0, this becomes also 0. So minus A, minus B, minus C also is equal to 0. And there is no contradiction. So, therefore, v1, v2, v3 are linearly independent. So we show that they are linearly independent. Last thing we need to show that they are v1, v2, v3 spans the kernel of T. To show that, we need to show that if we take any v inside of the kernel of T, say v is equal to x1, x2, x3, sorry, x0, x1, x2, and x3. Sorry, we are using the column vectors, so v is equal to x0, x1, x2, and x3. Say, and we need to show that we can express this v as combinations of v1, v2, v3. So this one is equal to x0, x1, x2, and x3. And since in the beginning we show that if an element belongs to T of v, x3 is equal to minus x1, minus x2, and minus x0. Here, instead of x3, I can write this one as minus x0, minus x1, and minus x2, right? As we show that. So this is equal to, let's write here, so this is equal to x0 times 1, 0, 0, minus 1 plus x1 times 0, 1, 0, minus plus x2 2 times 0, 0, 1, minus 1, 1 minus 1. So this is equal to V1, this is equal to V2, this is equal to V3. So this implies that V belongs to the set generated by V1, V2, V3, right? So this says that since V was arbitrary, we choose the V as arbitrary in the kernel. So the set V1, V2, V3 spans the kernel T. So basis for the kernel is equal to, therefore, we show that V1, V2, V3 spans the kernel, and V1, V2, V3 are linearly independent. Kernel belongs to V1, V2, V3. So this shows that the kernel of R transformation. Let's try to find the image of the R transformation. Now, let's look at T of 1, 0, 0, 0. Okay, this is an element of R4, right? T of 1, 0, 0 is equal to 1, right? 1 plus 0 plus 0 plus 0. So 1 belongs to image of T. So image of T is not equal to the set only consists of 0. So 0 is inside of the image of T, and image of T is inside the R, right? So since the 0 image of T is not equal to set generated by 0, and it's under the R, and the dimension of R, dimension of the real numbers, are equal to 1. So dimension of this 1 is equal to 0. So image of T must be dimension 1, and must be equal to R. So image of T is equal to R, and it's generated by 1. So basis for image is equal to set only consists of 1. So let's look at whether this set satisfies the rank nullity theorem or not. It must satisfy it, and it is not the part of the question. I just want to look at it. Rank nullity theorem. And rank nullity theorem says that dimension of space, if we take T is V from W, dimension of V must be equal to dimension image plus dimension kernel. In our case, our dimension is dimension of kernel is equal to dimension of kernel is equal to 3, right? Because the kernel, we find that basis for kernel consists of 3 elements. Where was it? Okay, I find it. Base of kernel consists of 3 elements. So dimension of kernel is equal to 3, and dimension of image is equal to 1, right? It only consists of 1 element. So dimension of image is equal to 1, and our dimension of R4 is equal to 4. So 4 is equal to 3 plus 1, So rank and nullity theorem satisfied. Rank, nullity satisfied. So this completes the part A. Question B is, in the question B, our transformation is a transformation from P3R to P3R where T of F is equal to F prime. And if you remember that, P3 elements of P3R are of the form A0 plus A1x plus A2x square plus A3x cube. And A0, A1, A2 and A3 are in real numbers. Now we need to find the kernel of this transformation. If we take any of these elements, let's take any if we take any vector in P3R, let's say B is equal to A0, A1x plus A2x squared plus A3x cube. And if we take the derivative of this one, let's not say B, let's say F. Take any F in P3R, and the derivative of F will be, this is F of x, derivative of F will be equal to, A0 will gone, right? When we take the derivative, A0 will become 0. So then we will have A1 plus 2A2x plus 3A3x squared. And we try to find where this one is equal to 0. So when this one is equal to 0, let's look at this one. So constant term here is 0, right? Here constant term 0, here constant term A1, and here constant term is 0. So A1 is equal to 0. Also A2 is equal to 0. And A3 is equal to 0. Again, the same thing. There is a term with x squared here. There is no term with x squared. So A3 is equal to 0. So A and A0 was arbitrary. A0 is arbitrary. So kernel of T is equal to F in P3R such that derivative of fx is equal to 0. So this is equal to, and since A1, A2 and A3 is equal to 0, this consists of only A0s. A0s are in R. So this set generated by 1. A basis of kernel consists of only 1. If you want that, you can show this one. You can show that this one generates the every 0 and 1 is independent. Show that this set is a basis. Now we also need to find the kernel. Now we need to find the image of this transformation. T is equal to T of F such that Fr in P3 of R. And when we take any arbitrary f here, we know that we will find a function like, and let's say, we will find the derivative of this f, so this one becomes a1 plus a2x plus a3x, 2a2x and 3a3x squared, a0, a1, a1, a2 and a3 are in R. So if you see that, this set can be generated by 1 and x and x squared. So basis for the image consists of the 1, x and x0. Please show that this is an basis for the image. So again, if you look at the rank nullity theorem, and dimension of this kernel is 1, right? And dimension of image is 3. So 1 plus 3 is equal to 4, and dimension of P3R is equal to 4, right? So rank nullity theorem satisfies in the set also. Our part C is T is a transformation from R2 to R2 where T tends to xy to 2x plus 3y and 4x plus 6y. Again, we are using the columns because the question uses the columns. So now first we need to find the kernel. Now let's look at the var. Take v in R2 such that t of v is equal to 0. So then, and say v is of the form xy. T of v is equal to t of xy, which is equal to 2x plus 3y, 4x plus 6y, which is equal to 0, 0, right? So from here, we have 2x plus 3y is equal to 0, and 4x plus 6y is equal to 0. As you can see that, this is the 2 times the first one, so we don't need to consider this one. So we only need to consider this one. This one is equal to 2x is equal to minus 3y. So x and y are dependent to each other. So if x is equal to 3, then y must be equal to minus 2, right? So take x is equal to 3, then y is equal to minus 2. So the vector 3 minus 2 belongs to kernel of t. Now we need to show that this vector generates the kernel, and since this is there is only one element, so we can say that this is independent. And let's say first independence. This is our v. The set consists of only v is independent. Why? Because c times v is equal to 0 for c not equal to 0 if and only if v is equal to 0, right? So this is okay. So second thing we need to show that 3 minus 2 generates this set generates the kernel of t. Let's look at in the other page. Now take any v in kernel of t. So v is equal to of the form xy Then this v is equal to, we can write this one as x and y is equal to 2x over minus 2, right? So this is equal to, and let's look at here. If we take, okay, this one can be expressed of 3 2 times something. Now there is an x here, let's say times x minus 3, and this x and y in R. So this is equal to something in R times this vector. So this v belongs to the subspace generated by 3 minus 2. So 3 minus 2 generates the kernel T. So basis of kernel T is equal to, the set consists of only 3 minus 3, and dimension of kernel is equal to 1. Now, before going on the kernel, I want to show you something. Now, dimension of space is 2, right? And dimension of kernel is equal to 1. So from the Brandt's theorem, we can see that dimension of image should be 1. Now we need to find the dimension of the image. If you look at the elements of the image, it should be, if we take any v, we will find an element like, say, v is equal to x and y. We will find an element of the form 2x plus 3y, 4x plus 6y, right? So if we take 2x plus 3y outside, we are taking any elements from the image. If you look at this T of B, this is equal to 2x times 3y, and this belongs to R. So we can see this one as a constant term, times 1, 2, right? So elements in the kernel are of the form, elements of the image are of the form 1, 2 times some constants, right? We can find any constant here and put anything in x and y. So T of B is generated by set consists, image. T of B is not a set. The set of the points in the image are generated by 1, 2, and 1, 2 is independent. Exercise, it's same with first case, I think, yes, it's only the set, since the set only consists of one element, this is independent, so basis of image is consists on 1. So also, if you remember again, dimension of the image is 1, dimension of kernel is 1, and dimension of R square is 2, so 2 is equal to 1 plus 1. Rank and Knowledge theorem satisfied. So this was the last part of the first question. Now, second question is, give an example of finite dimensional vector space V and a linear transformation T V to V, such that kernel of T is equal to image of T. More generally, for which values of dimension V can you find such an example? Now, first thing, we need to find a finite dimensional vector space V. Let's take our most common one, R2, right? R2 to R2. Please remind that finite dimensional does not mean the finite. Now, our vector space is R2, which is dimension 2. So this is finite dimensional vector space. Now, let's take AB from R2 and send this tuple to B0. So from here, show that this is a transformation. Exercise for you. This is a transformation. So, now, when this is a transformation, now we need to find the kernel and the image. Kernel of T is equal to tuples AB such that T of V is equal to 0, right? So this is the tuples AB such that T of AB is equal to B0. So B should be equal to 0, right? So this is equal to the set A0, A in R. So this set generated by 1, 0. And let's look at the images. Image of T is equal to T of AB's and B in R. So this is equal to T of AB is equal to B0. So B in R. So this set again generated by 1, 0, right? So they are the same. So since they are same, kernel of T is equal to image of T. So this completes the first part of the question. Now we need to find that for which values of dimension of B can we find such examples. Now, from Rank-Limited theorem, says as dimension of B is equal to dimension of kernel plus dimension of image, right? This was the Rank-Limited theorem. Now, since dimension of kernel and image is equal, this is equal to dimension of kernel plus image is equal to dimension of kernel. So this is equal to 2 times dimension of kernel. So dimension of V should be even. If dimension of V is odd, this gives us a contradiction, right? An odd number cannot be equal to 2 times an integer. You know that dimensions are always positive or 0 integers. So this gives us dimension of V should be even numbers. Can we find also now we need to show that can we find any such transformation for every V? Yes, let's say V is generated by V1 up to V2n, right? V2k, 2k is equal to n, and dimension of V is equal to n. Then we can write an as a transformation, like we can send without loss of generality, say T satisfies the transformation axioms. So this means that TV1 plus V2 is equal to TV1 plus TV2, and TCV1 is equal to C times TV1. Not VI. These are not the V1, V2, V3 above, let's say. Let's put dash here. These are not the same. So it is a transformation, and we can send V1 to 0 till we can send every element till TVN, Vn included, to 0, and we can send TVN plus 1 is equal to V1 to TV2n, which is n Vn plus n, right? So we can send this one S to Vn, and so dimension, kernel, and image is equal to V1 kernel and image generated by V1 up to Vn. So this completes the problem 2. Question 3. Let V be a vector space and T be a linear transformation on V. Show that the following are equivalent. A. Image T intersection with kernel T is 0. B. T of TV is equal to 0 if TV is equal to 0 for each V in V. Now, first thing we need to show that. Also, this is an exam question. Before this is exam question in, I think, from 2012. This was the exam question when I was a second year student here. So this was my exam question. So A implies B. First thing we need to show that A implies B. Now, first thing, we assume that image T intersection kernel T is equal to 0. And let's take B here. Let B in B such that T of TV is equal to 0. So this implies that since this is T of TV, right? So this TV should be inside kernel of T, right? And TV certainly is in the image of T, right? So since V in V, so TV and TV in image of T, right? There is nothing here. So TV in the kernel and TV in the image. Now, in here we are assume A, right? We are trying to A implies B. So, since A is true, TV in image of T intersection kernel of T, which is 0 set consistent only 0. So TV is equal to 0. So this implies that if T of TV is equal to 0, then TV is equal to 0 for every V in B. Now we need to show that B implies A. Again, let us take any V. Now we are assuming the B and we need to show A. V is in image T intersection kernel T. So Since B is in this intersection, this implies that B is equal to T of W for some W in V, since V is in the image, it's coming from here, and since V is in the kernel, TV is equal to 0. So let's look at T of V is equal to T of W, right? So since TV is equal to 0, this one is equal to 0. So T of W is equal to 0. So for now we assume the part B, right? T of W is equal to 0. This implies that T of W is equal to 0, which is V, right? So V is equal to 0. Since we take this V arbitrary inside of the intersection, this implies that intersection image T intersection kernel T is equal to set consists of only 0. Okay, question 4 is find linear transformation T1, T2 from R2 to R2 such that T1 composition with T2 is equal to 0, but T2 composition with T1 is not equal to 0. This will show that transformations does not need to commute each other. First, let's take T1 as the transformation as we take in the question 2, like from R2 to R2, AB goes to B0. T1 will be R2 to R2, AB goes to B0. And T2 will be, again, should be transformation from R2 to R2. And in this case, we will take AB to A0. Now, exercise show T1 and T2 are linear transformations. Now let's look at the T1 composition T2 AB. T2 sum to AB to A0, right? So T1 of A0, we will have T1 of A0, and T1 of A0 sums to 0, 0. So this is equal to 0. And let's look at the T2 composition T1 AB. So T1 goes to B0. So B0 goes to, again, B0. Since B is here, so B goes to here, and 0 goes to 0. And this is not equal to 0. So this is an example question asked us. Question 5. Suppose that A and B are n by n matrices and show that if A times B is equal to 0 and A is invertible, then B is equal to 0. Give an example to show that this statement is not true without the assumption that A is not invertible. First thing, we need to show that if A and B is equal to 0 and A is invertible, then B is 0. First thing, we need to show that this then. Now, A is invertible means that there exists A inverse such that A inverse times A is equal to identity, right? So, if you multiply with A inverse times, if you look at A inverse times AB is equal to A inverse times 0, which is 0, right? And A inverse times A is equal to identity times B. And identity times B is equal to B. So identity matrix times B is equal to B. So this implies that B is equal to 0. Let's give an example that this statement is not true without the assumption A is invertible. Now, let's take A, the matrix is this one. This matrix is like 0, all the entries except the 1n entry, A1n, and that entry is 1. And let's take B as the only non-zero entries is 1, A11, and the other ones are 0, and other entries are 0. So, and A times B, you can reduce that. A times B is equal to 0, but A is not equal to 0, and B is not equal to 0, and this A is not invertible. You can see that there is like row and the columns which are just 0. Okay, question 6 is, show that the determinant is non-zero if x1, x2, x3 are distinct numbers. Try to generalize to an m by n matrix M such that the ijth entry of this M is equal to xi to the g, xi to the power j minus 1. Now we need to find these determinants. Let's look at these determinants, okay? Now we have 1 x1 square, 1 x2 square, 1 x3 square, okay? Now we can subtract row 1 from row 2, and again we can subtract row 1 to row 2, and it does not change the determinant. Row 1 plus row 2 to row 2, row minus row 1 plus row 3 to row 3. So we will have, we didn't change anything in the row 1, 1, 1, 0, 0, 0, x2 minus x1, this 1 minus 1 is 0, x2 minus x1, x2 square minus x1 square. Here we have x3 minus x1, and here we have x3 square minus x1 square. Now, in this case, now we can do a row operation such that we can subtract minus x1 times r1 plus r2, and we can write, x1 times column 1, x1 times minus x1 times column 1 to column 2 to column 2. This again does not change the determinant, minus x1 square column 1 to minus x1 times column 2 to column 3, and we can write it to the column 3. Now let's look at here. Here we will have 1, 0, 0, and here we will have minus x1 times 1 is equal to minus x1, it gives us 0. 0 times minus x1 is 0, this does not change. Also this part does not change, x3 minus x1. Now we have minus x1 times column 2, minus x1 times 2 to here. So here we will have minus x1 times this one is equal to, minus x1 times this one is minus x1 square. So we have 0 here. Minus x1 square minus x1 square is 0. Here we have x2 square minus x1 square, and here we have minus x1 times plus x1 square. So plus x1 square minus x1 square is 0. x2 square minus x2, x1, right? So here we will have minus x1 times x3 times x1, and here we will have x3 square. Again, here we will have x1 square plus this one, we will have this one. Now, if you take this one to the x2 parentheses, you will have x2 minus x1, right? And here you will have, if you take x3 parentheses, we will have x3 minus x1. So, this column, this row, multiplied by x2 times x1, right? We have x2 times x1 here, we have x2 times x1, x2 minus x1 here, and we have x2 minus x1 here. So we will have also x2 minus x1 here. So we can take this x2 minus x1 outside. Then we will have here 0, 1, and x2 minus x1. And here we will have, here again, if you look at this row, and this row multiplied by x3 times x1, right? There is x3 times x1 also here. Also there is here x3 minus x1 times, we take this one also outside, 1 times x3 minus x1. Now I can also subtract row 2 from row 3. So minus row 2 plus row 3 to row 3. So I will have x3 minus x1 times x2 minus x1 times 1, 0, 0. This operation does not change the determinant, so 0, 1, x2 minus x1. So we will have 1, 0. So I will have x3 minus x1, there is plus x1, that gone, so we will have x3 minus x2. So this one is equal to, and also this row multiplied by x3 minus x2. So I will have x3 minus x1, x2 minus x1 times x3 minus x1 times this matrix, right? 1, 0, 0, 0, 1. x2 minus x1, 0, 0, 1. Now, so from the identity matrix, we only have this one, right? So if we add minus x2 minus x1 times row 3 to row 1, then we will get rid of this one, right? So if we say minus x2 minus x1 r3 plus r2 to r2, then we will have x3 minus x1 times x3 minus x2 times x2 minus x1 times 1, 0, 0, 0, 1, 0, 1, 0, 0, 1. So this is equal to, since this is the identity matrix and the determinant of the identity matrix is 1, so you will have x3 minus x1 times x3 minus x2 times x2 minus x1. So first part of the question is finished, but we have also second part. For the second part, answer is, I will give you a hint, which is the answer, then you should prove this one. The determinant of m is equal to, now if you look at that, it's x3 minus x1, x3 minus x2, x2 minus x1, right? This is the product of the differences, but there is an order between them. So if 1 less than equal to s is less than, strictly less than t, and less than equal to n, we have the product of xt minus xs. Product of differences with an order. So this completes the proof. Okay. And we have a triangle with three matrices with A1, B1, A2, B2, and A3, B3. So, the area of this triangle is equal to AX times A1 times B2, B3 plus A2 times B3 minus B1 plus A3 times B1 minus B2 over 2. Absolute value of this one. Now we need to find what is this determinant. Now let's look at this determinant. So this will we will have 1 over 2 A1 B1 1 A2 B2 1 A3 B3 1, and this is equal to. Now let's subtract this one from this one. Let's subtract row 1 from row 2 and row 1 from row 3. 1 over 2 is equal to A1 B1 1 A2 minus A1 B2 minus B1 0 A3 minus A1 B3 minus B1 0. So if we look at this column, if we take this column expansion, we will have first entry was 1, and if we delete this one and this one is equal to 1 over 2 times minus 1 to do 1 plus 3 times A2 A1 B2 B1 A3 A1 B3 B1. So this is equal to 1 over 2 times 1 over 2 times A2 A1 times B3 B1 minus A3 A1 times B2 B1. So this is equal to this is equal to 1 over 2 times let's look at, we have A2 here, right? So we will have A2 times, let's take A2 parentheses, there is no A3, B3 minus B1, and then we will have A3 here, so we will have like minus A3, let's say plus A3 times B1 minus B2 plus A1 times, here we have minus B3 plus B1, here we have B2 minus B1, so B1s are cancelled, so we will have B2 minus B3. So this is equal to this one. This is geometry. This is exercise for you. Using geometry, you can show that this area is equal to this one, but you need to show that with So absolute value of this one, let's take absolute values, then absolute value of this one is equal to same equation with the area. Question 8 is find the matrices of following linear transformations to the standard basis. Part A. T is a transformation from P to R to P to R given by Tpx of Px plus 1. Now, to the standard basis, right? Find the matrices following linear transformations to the standard basis. Standard basis on the P to R is, basis is 1, x, and x squared, right? This is the standard basis on P to R. Let's look at where 1 goes, where x goes, and where x squared goes. Now, P of 1 is equal to x plus 1, right? 1 plus 1 is equal to 2. So this is equal to 2 times 1. So let's look at the sorry. What am I talking about? This is the function, sorry. Sorry, do not make my mistake. This is not this is the function where every x goes to 1. This is a function. T of 1 goes, not the P of 1. This is T of 1. So 1 is the constant function, right? For every x, the function goes to 1. So P of x plus 1 also goes to 1. So T of 1 goes to 1. So 1 goes to 1. Let's look at T of 2. Sorry. T of x. I think I'm getting tired. So T of x goes to P of x goes to P of x plus 1, right? So the function x goes to x plus 1. Let's look at the where x squared goes. So x squared goes to x plus 1 square, right? We have P of x is equal to x squared. So P of x plus 1 is equal to x plus 1 square. So this is equal to x squared plus 2x plus 1. So we have, let's look at 1 goes to 1 times 1, right? This is, let's look at this one. This is 1 times 1 plus 0 times x plus 0 times x squared. 0 times x squared, right? So we have 1, 0, 0. We have 1, 0, 0. Let's look at here. X plus 1 is equal to 1 times 1 plus 1 times x plus 0 times x squared. So we have 1, 1, 0. 1, 1, 0. And this is equal to 1 times 1 plus 2 times x plus 1 times x squared, right? So we have 1, 2, 1. So matrix represented this linear transformation is this one. 1, 0, 0, 1, 1, 0, 1, 2, 1. Let's look at whether this one is correct or not. For example, if you take first generator, if you take this one, let's look at T of 1 is equal to 1, 0, 0, 1, 1, 0, 1, 2, 1 times 1 is 1, 0, 0, right? 1 is equal to 1, 0, 0. So this is equal to, wait a minute, there's a mistake here. Okay. This one times this one is 1, 0, 0, right? This one times this one is, sorry. What am I doing right now? This one times this one, 1 plus 0, 0, 0, 1. This one times this one is equal to 0. This one times this one is equal to 0, right? So it is equal to again 1, 0, 0. It's correct, right? So if you do that for x2, you will see that this one goes to this one. Let's check that this one is correct. Let's look at tx. Tx goes to 1, 1, 1, 0, 1, 2, 1, 0, 0, 1 times 0, 1, 0, right? So this goes to, so this one times this one gives us 1. And this one times this one again gives us 1. And this one times this one gives us 0. So again we will have, let's write this one as 0, 1, 0 goes to this one. Again this is 1, 0, 0. So let's also look at the t of 0, 0, 1 is equal to 1, 1, 1, 0, 1, 2, 0, 0, 1 times 0, 0, 1 is equal to, here this one times this one is equal to 1, this one times this one is equal to 2, this one times this one is equal to 0. So we find the right matrix. So this completes the part B. So part B is a transformation from R4 to R3 defined by t of x1, x2, x3 goes to x1. In the first tuple this goes to x1 minus x2 minus x3 minus x4. In the second place it goes to 2x1 plus x2 minus x3, and at second place it goes to x2 minus x3 plus x4. So now we need to find matrix representation for this transformation with the standard basis. Standard basis for R4 is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. And the standard basis for R3 is 1, 0, 0, 0, 1, 0, 0, 0, 1. These are the standard bases. Now we need to find that, what is this one? Let's say this one is V1. I don't want to write this one every time. V2, V3, V4. And this is W1, W2, and W3. Now we need to find this transformation and where they go. Let's look at, first we need to find TV1. TV1 is equal to, okay, we have 1 at the first component and 0 at the other component. So this one is equal to 1 minus 0 minus 0 minus 0. So it's equal to 1. Here we have 2 times 1, 2, plus 0 minus 0 is 0, 2. And here we will have 0, 0, 0. So we have 1, 2. So this is equal to 1 times W1 plus 2 times W2, and there is nothing in the third component, so 0 times V3. So for this one we have this one. For V2 we have, at V2 we have 1 at the second component, 0 at the other ones. So here we have 0 minus 1, 0, 0. So we have minus 1. Here we have 2 times 0 is 0, 1 minus 0 is 0. So here we have 1, 0, 0. So we have 1. So here we have minus 1 times V1, minus 1 in the first component, 1 times V2 times 1 times V3. So we have minus 1, 1, 1 as an coefficients. So So TV3 is equal to, and here for TV3 we have 0, 0, 1, 0. So here we have 0, 0, minus 1. So we have minus 1 here. So we have again minus 1 here. So we have again minus 1 here. So this is equal to minus 1 V1 minus 1 V2 minus 1 V3. So for V4 we will have 0, 0, 0, 1. Here we have minus 1. Here we don't have any x4, so this is 0. Here we have 1. So this is equal to minus V1 plus 0 times V2 plus 1 times V3. So our matrix will be, representative matrix will be, we have 1, 2, 0. We have 1, 2, 0 here. We have minus 1, 1, 1 here. And minus 1, minus 1, minus 1 here. We have minus 1, 0, 1 here. This is the representative matrix. Please check that. Check that. This one is the right matrix. Question 9. A linear transformation from R3 to R2 defined by sending t x1, x2, x3 to x1 minus x2 minus x3, comma, minus x1 plus x3. And let B and C be the ordered bases 2, 0, 0, minus 1, 0, 1, 1, 1, and 0, minus 1, and 1, 2 of R3 and R2 respectively. Find the matrix that represent T with respect to these bases. Now, in the previous question we have standard bases, but in this question we don't have the standard base. We need to find the matrix corresponding to this matrix. So do not try to find the matrix always with using the standard basis. So let's look at. Again, I want to say V1, V2, V3. Like, if you're confused about why, also before starting from the question, why I use the columns and why I use the rows here, because the question gives myself, like there is no difference between them. So here we have V1, V2, V3. Here I say, let's say W1 and W2. Let's look at T of B1 goes to where? T of B1, so here we have 2 in the first component and the 0 otherwise. Here we have 2 here, 2 minus 0, 0, and minus 2, 0. This is minus, if you're confused about it, this is minus x1. So we have minus 2. So we need to find this one here. So here we have 0. So here we have 2. So 2 must come from here. So 2 in the first component must becomes here. So we have, so we should have 0 minus 1, something plus something, 1, 2. So we have 2 here. There is nothing here, so 2 must come here. We have 2. So we have 4 here. But we have minus 2 here. So we should have minus 6 here. So, plus 6 here. So, minus 6 plus 4 gives us minus 2. Let's look at the T of B2. And this goes to minus 1 minus 2 is equal to minus 3, comma, and again minus 1 times minus is 1, so we have, and x3 is 0, so we have 1 only. Now again we need to find the coefficients of this one. Now for this one we have minus 3 here, right? Again we have 0 here, so this should be minus 3. So we have minus 6 here. But since we have minus 6 here, we need to find 1 here. So we should have minus 7 here. So minus 7 times minus 1 is 7. 7 plus 6 gives us 1. Let's look at T of V3. T of V3 is equal to, now we have 1, 1, 1. So 1 minus 1 is equal to minus 1. And minus 1 plus 1 is 0. So it is equal to 0. Again, we need to find the coefficient of these two. Now, here we have again minus 1. There is nothing coming from here, so we should have minus 1 here. So we have minus 2 here, and we have 0 here. We should put something here, so it should be cancels that one. So we have minus 2 here, we should have plus 2 here, so we need to find minus 2. So minus 2 times minus 1 is equal to 2, so 2 minus 2 gives us 0. So basis should be, matrix should be 6, 2, minus 7, minus 3, minus 2, minus 1. So please exercise, check this is true. Is the right one.